Hi, I'm Gary GB Educat, and today I'm going to be presenting column vectors. So when we're talking about vectors, we're actually talking about a quantity which has magnitude and direction. So in many cases, we're talking about a line which has a distance and it has a direction which it's traveling from. When we are traveling away from a start to a finish, this is called displacement. So when we're talking about a vector notation, some of you may know it as column vector notation. We are talking almost, you might have seen coordinates where rather than numbers being next to each other, they're actually on top of each other, much like this. This is a column vector, which is telling us the direction that we are going to be moving in. So the 3 means that I'm going to be moving to the right by 3. The 2 means that I'm going to be moving up. So long and short is that the top number, if it's positive, we're going to move to the right. If it's negative, we're going to move to the left. The bottom number, if it's positive, we're going to move up. If it's negative, we're going to move down. So as a visual for this, here I've got AB, where I'm moving in the direction of AB, where 3 is telling me to go to the right by 3, and then go up by 2. That's taking me from A to B. So the direction of the line is given by this arrow just here. So I'm moving from A to B. And the magnitude is the length of the line. So when we're talking about vectors, you'll see them a lot written with the letters and an arrow written on top. This is telling you where you are, your starting point and your finishing point, which direction you are going. Sometimes you can see the lines with a letter there, or you could see it if it's written as a letter with either an underline or a little squiggly line just written underneath this. If we've got a line which has got the same magnitude and the same direction as another line, these two lines are parallel. Now, as opposed to if we're travelling from A to B, this we note as A. If we're travelling in the opposite direction from B to A, this is going to be negative A because we're travelling in the opposite direction. And as you can see here, the vector would actually have the values as opposite because we would go down by 2, so it'd be negative 2, and we go to the left by 3, so it'd be negative 3, negative 3, negative 2. So when we're dealing with the column vectors and the magnitude of vectors, we can actually increase or decrease these using a scalar. But when we're using scalars, this only changes the magnitude. It changes the length of the line. It will not change the direction of the line. So as an example, here I've got A and 2A, but 2A is twice as long as A. So A is the vector 3, 2. 2A is 6, 4. So we've taken both of our values of our vector and we've doubled these. So 3 doubled gives me 6, 2 doubled gives me 4. We can also add or subtract vectors, which is the exact same as adding a vector to another or removing one away from this, taking it away. For our example for this, we've got S, which is a vector of 5, 2. Sorry, 5, 3. So cross by 5 and then up by 3. And we've got a vector of T, which is 3 to the right and then 2 down. So 3, negative 2. Now I could add these by simply taking my horizontal vectors, my top numbers, adding those together, and then adding together my bottom vectors, which will give me a vector of 8, 1. And I can confirm this because get from this point to this point will be 1, 2, 3, 4, 5, 6, 7, 8 across. So 8 works, and then 1 up. So positive 1 would be underneath. I could also subtract vectors. So I'm using much the same example here, but this time I'm going to be subtracting my S and my T. So I've got my vector for S, which is 8, 1. I've got my vector for T, which is 3, negative 2. And subtracting these away from each other, so doing much the same as what I did with addition, but I'm subtracting my top numbers, subtracting my bottom numbers, that gives me a vector of 5, 3. And I know this is correct because it's the same as what I've got above, and S was 5, 3 for above. We could also use Pythagoras to find the length of a line. So vector A for this, we could use the fact that we could use 3 and 2 within our Pythagoras theorem. Reminder of Pythagoras theorem is c squared equals a squared plus b squared, where c is always your hypotenuse, your longest length of your right angle triangle. And often you'll see this written as a modulus. By this I just mean with a line either side of the A. So modular A is going to, by this I mean the magnitude of my length A is going to be 2 squared plus 3 squared, which gives me the square root of 13. So this is my exact value, but if I wanted to round this, I could give this as 3.61 units to 2 decimal places. There is also a parallelogram law when we're talking about vector addition. So here I've got a parallelogram just here, where I've got from D to F, using my direction from D to F, I could use my direction A plus B for this. But this is going to be the exact same as if I went from D to G and then G to F. It will be the exact same results. So I can label the opposites as A and the opposites as B for this. Because when we're talking about addition, addition is commutative, in which case it doesn't matter what order we do addition in, it still works. So with this we can go A plus B, or we can go B plus A. It gives us the exact same outcome. We can also do some problem solving when we've got vectors. So here I've got a small triangle of APQ, and I've got a similar triangle, a larger triangle of ABC. And from this, I'm going to be, it's giving me some information that PQ, the line PQ is such that P is the midpoint of A and B, Q is the midpoint of A and C, and using the vectors to show that PQ is parallel to BC. And also to show that the length BC is double that of PQ. So I'm going to be using a bit of a proof for this. So I'm going to call my vectors here from A to P, A, from A to Q, E. And I'm going to be using these letters to actually solve the rest to prove this. So from P to Q is going to be minus AB, because I'm going to get from P to Q, I'm going to go in this direction first, so it's going to be minus A, and then in this direction, so it's going to be positive B. So I'm just rearrange that to B minus A. To get from B to C is going to be minus 2A, negative 2A, because if P is the midpoint of AB, that means this length here must be the exact same as this length here. And exact same for Q, this length here of AQ must be the same length as QC. So I've got negative 2A plus 2B to get from B to C. So as you can probably see straight away, if we was to factorise this, taking the common factor of 2A to this, we get 2A inside the bracket and B minus A inside the bracket. Now, therefore, BC is going to be half the size of PQ. So you got 2PQ is equal to BC, the direction of these. Therefore, you can actually confirm all this, that BC is double the length of PQ, and because they've got the same magnitude, they are also parallel. You can also rearrange these in very similar ways what you do with equations. So here we're going to find vector C such that 2C plus A equals B, where A is minus 4, 7 and B is 6 minus 1. So what we're going to do, first of all, we're going to rearrange this to make C the subject in much the same way as what we would do in an equation. So just starting off with 2c plus a equals b. If I subtract a from both sides, I've got 2c equals b minus a. Now, if I was to divide both sides by 2, I've got c on itself on the left-hand side. On the right-hand side, I've got b minus a over 2, so halved. Now, if I substitute in my values, here I've got my values for my vector b, replacing my b, so 6 minus my negative 4 for my top number of my vector a, and I've got minus 1, the bottom number of my vector b, subtract my 7, which is my bottom number of my vector a. So that's going to equal a half times 10 minus 8, which of course is going to halve both of these, which is going to leave 5 negative 4 as my vector. If you like what you see, please remember to subscribe. Thank you very much for watching.